Hello, everyone. My name is Daniel Mesheske. I am a PhD candidate in the Civil Engineering and Environmental Science Department here at the University of Oklahoma. First, I'd like to thank the conference organizers for allowing me to speak today. And I would also like to thank my co-authors, Dr. Jeffrey Basara and Dr. Jordan Christian, who assisted with this research. Today, we'll be looking at the seasonal and interseasonal relationships between atmospheric and surface variables in Europe. So this project was born out of the idea of looking at the drivers of flash drought. Flash drought is the rapid intensification of drought-like conditions. This phenomenon is largely driven by atmospheric demand. However, the extent of that demand can be influenced by many other factors such as temperature or humidity. This high atmospheric demand can very quickly desiccate soils, which results in high level of vegetative stress, which can be very harmful in many agricultural sectors. So this flash drought is the development of meteorological drought conditions that very, very quickly will move into agricultural drought. The primary goals of this project were to better establish and to quantify relationships between atmospheric variables, such as temperature, vapor pressure deficit, evaporative stress, with surface variables such as root zone soil moisture on a large temporal and spatial timescale. And then from that, we want to see if these relationships will give us some sort of a signal that we can use to predict subsequent drought risks. And lastly, to look at our standardized evaporative stress ratio as sort of a proxy bridge between the atmospheric variables and soil moisture, which can be somewhat problematic, as we will talk about coming up. The data used for this analysis was downloaded from NASA's MERIT-2 reanalysis archive. All of the data that we used were daily mean values from January 1st, 1980 to the end of December in 2020, which gives us a total of 41 years. The main variables we used were 2-meter temperature, 2-meter dew point temperature, evapotranspiration, and root zone soil moisture. There were some other variables that we used, but those are largely used to calculate our potential evapotranspiration using the Penman-Monteith FAO formula. Finally, we took the evapotranspiration and the potential evapotranspiration and calculated our standardized evaporative stress ratio, also known as CESR. CESR was developed by Dr. Jordan Christian as a way to measure atmospheric demand anomalies. So these daily mean values that we collected were combined to create single seasonal values for each of the 41 years. So we'd have 41 values, one for each spring, each summer, and each fall. Then the seasonal time series were standardized and detrended to create anomaly values. So here we can see an example from a random grid point that exhibits the yearly seasonal anomalies for both our CESR and our temperature. Then we took these time series on a grid point by grid point basis for the entire study area, and then compared them through linear regression, and then calculated correlation coefficients, and finally subjected these correlation coefficients to a T-score significance test. T-score testing was done at multiple levels of significance to try and better understand the significance of these relationships. So there is a well-known relationship between temperature, evaporation, and soil moisture with feedbacks that go in both positive and negative directions. Direct correlation of temperature with root zone soil moisture can be problematic, particularly at large spatial scales. This is most likely due to variation in soil properties such as soil type, mineral content, specific capacity, and porosity, and etc. But it'll also be affected by local climatic conditions. This plot shows the correlation of temperature with root zone soil moisture. And as we can see, there's some both positive and negative correlations, but we don't see as high levels of significance. It's difficult to see, but there is a stipple that's overlaid where the grid point T-score tests scored above 90% significance. And as you can all see, there are very, very few. But when we plot the seasonal correlations of temperature with Caesar, our measure of evaporative demand, we see there's something very different. In both spring and summer, we find that there is a very strong negative correlation. This kind of reinforces what we'd expect. Lower values of Caesar represent higher evaporative demand because the standardized ratio of ET to PET, meaning that lower values indicate higher levels of potential evapotranspiration. So the top plots have an overlay of the grid points where the T-scores show significance at over 90%. And as we can see in both seasons, spring and summer, that this relationship proves to be extremely strong for the entire continent. So our correlation between evaporative demand and root zone soil moisture, though, is not quite as strong. However, it does show better results than the direct correlation of temperature and soil moisture. We still see a lot of regional variation in both positive and negative correlations, but we also see many more areas of statistical significance. As temperature and Caesar are so strongly correlated, as we just saw, it would be fair to say that in some of these areas where there is strong statistical significance in this plot, that temperature and root zone soil moisture have a stronger relationship. Now we get to what I think is the exciting part. Here we introduced a one-season lag into the regression. So now we're comparing spring and summer temperature, respectively, with summer and fall evaporative demand, respectively. So we can see that there's still a very strong negative correlation for much of the map in both seasons, with strong levels of statistical significance. Interesting of note is when the seasonal lag is introduced, areas of higher latitudes and areas of higher elevation, the statistical relationship seems to break down. So areas such as the Balkans and the Alps no longer show significance. This could be because of cooler temperatures, both later in the spring or possibly earlier in the fall. What we also see is there is a band that runs across the middle of the continent that shows high levels of significance. And as we move from summer to fall, we see that this band shifts somewhat northward. The bottom, we also see the vapor pressure deficit. We're not going to talk about that very much because it's very similar to temperature, as temperature is used to calculate it. So we see that the maps are almost identical. Using these plots, though, it suggests that we can use the mean seasonal temperature to infer what evaporative demand is going to look like in the following season. Because flash drought is largely driven by evaporative demand, this lag relationship could be used as a possible baseline in combination with other variables to help predict the likelihood of a flash drought occurrence. So once lag is introduced to our Caesar and root zone correlations, we still see a lot of regional variation, both positive and negative. However, there is more statistical significance when the lag is introduced than when correlating within the same season. This may be due to a lag time between changes in evaporative demand and changes in level of soil moisture. Again, we see particularly in some regions, particularly in the central part of the continent, that there are areas where elevated levels of evaporative demand have a very strong influence on soil moisture. Because of the strong relationship we establish between temperature and evaporative demand, we can possibly infer that those areas would have increased soil sensitivity to increases in temperature and would be more likely to experience a flash drought during these particular seasons. So the main takeaways would be that atmospheric temperature and vapor pressure deficit have a significant concurrent and interseasonal relationship with our evaporative demand, our standardized evaporative demand. Also, that evaporative demand has a regional relationship with root zone soil moisture, with that a relationship increasing in strength and statistical significance interseasonally when lag is introduced. We also see that we can possibly in some regions use Caesar as a bridge between temperature and root zone soil moisture that can be used as an indicator of areas that may be more prone to flash drought. So look at some future work. This is somewhat of a teaser here, but we started to do these same analysis in other geographic regions. And you can see that this same sort of response we have in some areas of the United States when we do an interseasonal relationship, again, between temperature and evaporative demand. We see particularly spring, summer through the Corn Belt, and then summer, fall through the Southeast. So focusing on some of these localities of higher significance, we plan to examine regional soil effects and to bring in some other variables that may increase our ability to predict flash drought. Thank you all very much for your time, and I will be happy to answer any questions that any of you may have.